Okay. I see we've got 3 people logged in. Can you guys hear me? If so, type in the chat window. You don't have to turn your microphones on unless you want to. Okay, Hannah can hear me? Cool. All right. So, you guys have any questions? Cool. Okay. All right. So basically, I just figured I'd answer questions. So feel free to type them in the chat window, or if you want to speak it, just turn your microphone on for a minute and say your question.
Okay, can you hear me?
I can hear you, Hannah. Yep.
Oh, awesome. I was wondering if we could just do another problem like the disk, and it's number it's number 2 on one of the exams, but if we could do a disk and a ring
Oh,
problem, like work.
yeah. Okay. All right. So let
Okay.
me see. I've written down those. Let's see. I don't think you guys can see the main screen. Let me turn on the main screen for a second. If I can figure out how. Well, no, it doesn't want to do that. Can you guys see the main screen, or can you just see the document camera?
Wherever your hand just was.
Okay, that's all you can see. Okay. All right. So let me write down the equations over in the corner here. So we know for a point charge, we've got K Q over R squared is our electric field. So point charge. And let's see. So a wire, we've got an electric field of K Q over Y, 1 over L squared plus Y squared, square rooted, where L is 1/2 the length of the wire, and Y is whatever distance above it we're trying to measure. And then we've got the equation for a ring, which is K Q Y over R squared plus Y squared to the 3/2 power. So that's for a ring of radius R at some distance Y above it. And then we've got a disk of charge, so a solid disk of charge at some distance Y and some radius R. E equals 2 pi K sigma 1 minus Y over R squared plus Y squared square rooted, like that. Okay. So you guys do not need to memorize those. I'm just going to give you a sheet of paper with all 4 of those on there and the explanation of which ones are which. Okay, and so if we want to do an example of this, so a typical example would be any combination of these 4 things. So let's give ourselves a x-axis over here, and this is our y-axis. And let's put a disk of charge over here at x equals 2 centimeters, with some radius big R is equal to 10 centimeters. And let's put a hoop on here with radius little r equals 5 centimeters, located at x is 7 centimeters, and a point charge over here, P, with a certain charge C, and this is going to have some charge B, and this is going to have some charge A on it. All right, let's say the charge A is plus 15 microcoulombs. Charge B is minus 20 microcoulombs, and charge C is 7 microcoulombs. Positive. All right, so we want to find the electric field at C and then probably the force at C, which is just equal to the charge of C times the electric field located at C. And I have to give a location for this. Let's put this at x equals 13 centimeters. All right, so it's just a matter of finding the field due to the disk at this location and adding the field due to the ring at that location. All right, so let's see how we would do this. The electric field due to this disk at some distance away from the disk equal to R1, and then this distance here for the ring is some R2. Okay, so let's just figure them out and add them together. But before we do that, let's figure out which one's positive and which one's negative. At the location of C, let's ignore the fact that there's a charge there. Let's just pretend there's no charge there right now. We want to find the direction of the electric field. So the disk has a charge of QA, which is positive, so it points directly away from the disk. So at this location, it's going to point away from the disk, the E field due to the disk. And the ring has a negative net charge. It's going to point towards the ring in any direction. So here it's going to be E towards the ring. So we're going to have a positive electric field due to the disk, because it points in our positive x direction, and a negative electric field due to the ring that points in the right-hand direction, or sorry, to the left.
Wait, how did you know that the ring is negative?
I defined that over here. It's got some QB on it, and I said, let's call that
Oh,
negative.
it's
Yep.
funny. I didn't see.
Yep.
Okay, thank you.
Yep. Feel free to interrupt at any point if I'm being confusing. Okay. Let's see. Oh, that was a question mark. All right. So we want to find the electric field due to the disk and then subtract the electric field due to the ring at this location over here. So the electric field due to a disk, as we saw above, is 2 pi k sigma 1 minus y over r squared plus y squared, and then square rooted. All right, so let's write this down. We've got 2 pi k sigma 1 minus y over r squared plus y squared, and then we square root that. Okay, so we've got 2 pi, and k is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And then we've got sigma. Now remember, sigma is our charge density on an object, so that has some, let's see, charge density Q over A, where we've got the charge on the entire thing, QA, which is plus 15 microcoulombs, so 15 times 10 to the minus 6 coulombs. And we're going to divide that by the area, which is 2 pi r, since it's a solid disk, or sorry, no, pi r squared, which is going to be divided by pi, and then the radius of that we said was 10 centimeters, 0.10 meters squared. All right, so if I put that in my calculator, let's see, so that would give us 15 e to the minus 6 divided by pi times 0.1 squared. So this has a sigma of 4.77 times 10 to the minus 4 coulombs per meter squared. All right, so that's the number we're going to put in here, 4.77 times 10 to the minus 4 coulombs per meter squared. And then we're going to multiply it by 1 minus y, which is the distance between the center of the disk and where we're measuring it over here. We said that was 2 centimeters. This one's at 13, so the distance is 11 centimeters, or 0.11 meters, divided by, let's see, big R squared, which is the radius of the disk, because that's the one we're finding the field of. So 0.10 meters squared plus the 11 centimeters, 0.11 meters squared, square rooted. Okay, and then we plug that all into our calculator. Let's see, 2 times pi times 8.99 e to the 9th times 4.77 e to the minus 4 times 1 minus 11 divided by, or 0.11 divided by 0.1 to the second plus 0.11 to the second. And I get an electric field due to the disk of 7.01 times 10 to the 6th newtons per coulomb. Okay, and this is a positive number, which means, we're always going to get a positive number out of here, sorry. But it was a positively charged disk, which means it's pointing away at that location, so it's pointing in the positive I direction. Okay, if anybody's confused so far, just write something in the chat window or speak up. All right, so we found the field due to the disk. Now we just need to find the field due to the ring and subtract them, because we know the ring points in the other direction. All right, the field due to a ring is k q y over r squared plus y squared to the 3/2 power. All right, so that is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. We're going to multiply it by the absolute value of the charge on the ring, which would be 20 times 10 to the minus 6 coulombs. Then we're going to multiply it by the y value. So that's the distance between where we're measuring it and the center of the ring over here. So let's see. So that's going to be 13 centimeters minus 7 centimeters, 0.06 meters, divided by the radius, and this time it's the radius of the ring, because that's the one causing the field, 0.05 meters squared plus 0.06 meters squared, and that entire thing to the 3/2 power. Okay, so when we plug that in, what do we get? 9 e to the 9th times 20 e to the -6 times 0.06 divided by 0.05 to the second plus 0.06 to the second to the 3/2 power. All right, and I get 2.26 times 10 to the 7th newtons per coulomb, and this is in the minus I hat direction because we figured that out from over here. It's a negatively charged one, so we have to stick in the minus sign at this point because remember, the equation won't give it to you. It'll always give you a positive number. All right, so the only thing left to do to find the electric field at this point P is to add these together. So we're going to do E of the disk plus E of the ring, which will give us 7.01 times 10 to the 6th newtons per coulomb minus 2.26 times 10 to the 7th newtons per coulomb. All right, 7.01 6 minus 2.26 e to the 6. Okay, and, oh, nope, wait, what did I do wrong? Oh, hold on. Okay, that gives us 4.75 times e to the 6th newtons per coulomb. So that would be our electric field at point P. And it's going to point in the positive I hat direction because the positive number here was larger than the negative, so I ended up with a positive I hat direction. And then the force is simply QC, whatever charge is located at C, if any, times the field. All right, so we said QC was positive 7 times 10 to the -6 coulombs. Our field is 4.75 times 10 to the 6 newtons per coulomb. So we're going to get 7 to the -6 times 4.75 e to the 6 gives us 33.25 newtons. And since this is a positive number, we haven't changed the direction of our field, so our force is also pointing in the positive I hat direction. So that would be our electric force. And this is our field. So whenever you've got a combination of several objects, several point particles, several actual objects, all you have to do is put them in the same direction. Let's see, big Q and little q, is there a difference between them? Okay, so when you're looking at the E field due to an object, a point charge, a disk, a ring, a line, the Q in that equation is always the object's charge itself, because the electric field doesn't depend on anything being at the other location. The only time the charge of something at the location matters is if you're calculating a force. So when you're calculating a force, then it's this little Q over here. All these Q's over here, whether they're big, small, doesn't matter. It's always the charge of the object itself that goes into that one, because the electric field doesn't care if there's anything else there. Any other questions? Or are there any questions on this before we move on? Or just any?
No, that's helpful. Thank you.
That's great. Okay, cool. Great. Any other questions you'd like to go over? Okay, rho and sigma. So let's remind ourselves how those work. So if you've got charge on an object, you can either have a line or you can have a surface. Let's call this a line. This is a surface. Or you could have a volume, like say a cube or something. All right, when we're talking about the charge sitting on a line, we say that we've got some linear charge density lambda. Linear charge density lambda. And basically lambda is just the total charge on the object divided by the length of the object. So L, there's some Q on it, and lambda is charge per unit length. So whenever we're talking about a one-dimensional object, we'll talk about lambda. Surface, we've got sigma, where that's our surface charge density. Sigma. So sigma is equal to the amount of charge we have divided by the area of the object. So this is its area, and Q is sitting on there. So our surface charge density. And then for volume, we have a volume charge density, rho. Rho, where rho is the charge divided by the entire volume. So it's the charge on the object divided by the volume of the object in total. So you might want to have equations written down for the volume of a sphere, the volume of a cylinder, surface area of a sphere, surface area of a cylinder. Those tend to come in useful. Any other questions about these charges? Now, the other thing to remember, if you have a conductor, even if you have a volume, so say a sphere, all of the charge is going to be sitting on the surface. All charge on surface. So, even if your conductor is a physical volume, you're only ever going to talk about either a linear charge density or a surface charge density, only for a conductor. You'll never talk about a volume charge density because in the electrostatic sense, we'll never have any charges inside the volume. They want to get as far away from each other as possible, and they all end up on the surface. But if you've got an insulator, you can end up with charges distributed throughout a line, or an area, or a surface. So you can end up with lambda, sigma, or rho. All of these are possible for an insulator. Okay. All right, are there any other questions? Anything on the homework or the handouts that we looked at that people are confused on? Yeah, okay. So the definition of flux. All right, so we had two different ways to define our electric flux, which is this one right here. Flux, well, electric specifically, because we might run into magnetic depending on how much time we have. Okay, so our electric flux, if you think of it going through some sort of area, you could define it as E dot A, where this is the dot product of the electric field and an area vector from the surface, which reduces to EA cosine of the angle from E to A, as long as you've got a constant field over your surface and a constant angle between your electric field and your area vector. So if you had, say, the electric field heading off in this direction over here, and you had, let's say, a sheet of paper or maybe a hoop you were putting in here, a circular hoop, that was lying in the same field as this, so the E field due to the hoop would point straight, let's see, the E field from the thing is pointing over here, the area vector from the hoop is pointing straight up. If the vector between these two were equal to 90 degrees, then you've got the cosine of 90, which is equal to 0. So when E is perpendicular to A, you've got no flux. On the other hand, when E is parallel to A, so that would be a case of an electric field off in this direction, and then maybe putting your hoop in it here, so the A vector points in the same direction as the field, then you've got the max flux. And then somewhere in between, if you took your hoop and tilted it one way or another, you'd have slightly more or slightly less flux. So that's one way to define the flux. Our other definition for the flux is simply all the enclosed charge inside our Gaussian sphere divided by sigma naught. Or, sorry, I think that's an epsilon naught. All right, which is simply a constant. So you can define this either way, and we got Gauss's law basically by setting these equal to each other. EA equals Q enclosed over epsilon naught. And for here, we usually ignore the phi because we've always dealt with a case where it's either parallel or perpendicular. So if it's perpendicular, it's 0. If it's parallel, it's E times A. Yep. So I could give you something like 3 charges, QA, QB, and QC, and draw a Gaussian surface over here and say, calculate the flux through the box. Well, the flux through the box is simply add up the enclosed charges and divide it by epsilon naught. Or I could give you a constant field and a object sitting in it and say, okay, well, find the flux through the object, then you've got the EA cosine 0, or cosine phi problem. Either of those are easy ways to ask for the flux. Yep, exactly. So QA isn't inside our Gaussian surface, so it doesn't contribute to the flux. If it's a positive QA, remember its electric field lines point away in every direction. They would go into the box, but then they'd come out again. So it's only ones that originate in the box or end in the box that matter. Yep. So if it's not inside your Gaussian surface, you can't see it. You can ignore it entirely. All right, any other flux questions? Or
So the
questions?
Q enclosed on that one,
Yeah.
you would just add up whatever QC and QB are?
Yes, because they're the only ones in the box I drew. If I drew this box instead, then you'd add up everything in that box, which is QC and QA instead. And remember, the box itself, it doesn't matter what that looks like. It only matters what's inside the box.
And there would be no area factored in there for the Q enclosed?
Not here. Usually when we worry about Q enclosed, we're talking about Gauss's law. So at that point, we'd have to say, all right, well, there's some charge in here somewhere, but maybe it's only distributed on a certain shape, and it's got some area associated with it and some charge density. So to find the Q enclosed, we would need to rearrange our charge density and sigma equation. So if we had a sigma and an area, we would find our Q enclosed by saying, oh, well, it's just sigma times A. You guys want to go over a Gauss's law problem so you can see that?
Sure.
Okay. I think there's one complicated version that we didn't take a look at yet, and that would be a multi-level cylinder. All right, so let's say that we have a infinite cylinder, so this would just keep going in each direction out here, and it's made of a conductor. And if this is the center, it's got a radius A. And around it, I'm going to put an insulating material out here at some radius B. And this one is an insulator. Okay, and I'm going to find my electric field at 3 different places. I want to find it at R1, which is inside the interior conductor, R2, which extends from the middle out to the middle of the insulator somewhere, and R3, which would go all the way outside our conductor. So basically, I'm going to draw myself 3 Gaussian surfaces. One in here with a radius of R1, one out here with a radius of R2, and one all the way out here with a radius of R3. And I'm going to give them all the same length, but they don't have to have that, some length off. All right, so let's say I wanted you guys to find, let's see. So I said this was the conductor on the inside and the insulator on the outside. So I want you to find an expression for the electric field at R1, R2, and R3. And then we'll try plotting them and see what they look like. All right, so the electric field at R1 times the area is equal to the enclosed charge over epsilon naught. Now this is the area of our Gaussian cylinder at R1, so this is our little one in here. And this is the charge enclosed by our Gaussian cylinder divided by a constant. All right, now before we even get to this point, we've made some sort of assumption. We've made an assumption that a cylinder is a good Gaussian surface to put around another cylinder. And that's a very good assumption as long as you line them up so that they have the same middle axis. You don't want to take these cylinders and flip them on their side. That's not going to help. All right, and the reason we did that is that the electric field from our actual object here is going to be parallel to our area vector coming away from our object, at least from the curved sides. So the curved sides of Gaussian surface have E is parallel to A. So we've got max flux. But on the end caps, the area vector points out this way, but our electric field is still pointing straight away from our charge up this way. So we've got E is perpendicular to A, no flux through end caps. Which means only the sides with flux through them are going to be contributing to our area and our Q enclosed. So our area is only the end caps, which have a radius of R1. And there are 2 of them, so it's going to be 2 pi R1 squared. That's the area of our Gaussian surface at R1. Our Q enclosed is going to be everything inside this cylinder. All right, now this is a solid conducting cylinder. But remember, conductors only have charge on the outside surface. So we're not going to worry about anything that we find inside. We can go out from the middle of this as far as we want, and as long as we haven't hit the outside surface yet, we don't see any excess charge. We have an equal amount of positive and negative charge inside our cylinder. So there's actually no excess charge in here. All the positives and negatives cancel out. And if Q enclosed is equal to 0, that means E, R1, is equal to 0. There is no electric field inside a conductor unless you actually put some charge in there. Like if I put a line of charge through here somewhere, then I could have some field charge in there. But if it's just inside a solid conductor, you've got no electric field due to the conductor. So in this case, it's equal to 0. Okay, let's find our electric field at R2 times the Gaussian surface at R2 equals Q enclosed over epsilon naught. All right, our Gaussian surface at R2 has the same conditions as our one up here. So we're looking at the end caps again. 2 pi R2 squared is our area of our Gaussian surface. Our enclosed charge at this point, if we go out to R2, which is this one right here, this cylinder in the middle, basically we've taken up the entire conductor and we've moved past the surface, so now we need to worry about the surface, and we've moved out into the insulator. So this is going to be part of the conductor plus part of the charge on the insulator. All right, so the charge on the conductor only sits on the surface, so this is going to be some sigma A of the surface, and then we're going to add in rho volume of the insulator inside. So insulator enclosed. All right, so our Q enclosed is going to be sigma, which is the charge on the outside surface of this conductor, times the area of that surface. Okay. Oh, wait. Sorry, you guys should have interrupted me. I said the flux through the end caps doesn't matter, and then the only flux I'm counting is for the end caps. Okay, that's not the area we want. We don't want the area of the end caps. All right, we want the area of the curved surface only, which is going to be the circumference times the length. So this up here, although it doesn't matter, should have been 2 pi R1 L. And this one over here, which does matter, area of our Gaussian surface, is 2 pi R2 times L. All right, so it's only the curve. Sorry? Yep.
You don't want the impact because the angles, they're perpendicular?
Exactly. So there's no flux.
You want
Yeah, we just want the curved side. Yep. Because that's the only
because that's the cosine of 90.
Yeah, this over here would be cosine of 90, which is 0. This is going to be cosine of 0, which is 1.
1. Okay, perfect. Thank you.
Okay, sorry about that. All right, so 2 pi r L squared. All right, so this is going to be times the area of the conductor that's inside our Gaussian surface. So that's basically this part down to this part here. So it is the outside area of the curved surface of the conductor, which is going to be 2 pi times the radius of the conductor, which is little a right here. 2 pi a times the length of our conductor. Okay, so this is the area of the conductor included inside of our Gaussian surface of 2 pi little r to L times the charge on that surface. And then we're going to add in rho times the volume of the insulator that's enclosed. All right, so basically we have part of an insulator, like a thick tube, but the inside of it is empty. So we need to subtract we'd have to take the volume of the large insulator and subtract the volume of the small insulator. The large insulator only goes out to R2. So the volume of a cylinder, let's see, the volume of a cylinder is going to be the area of the end caps times the length. So it's going to be pi sum r squared L. So the volume of the cylinder with an end cap that goes out to R2 would be pi R2 squared times L. This is the volume of a large cylinder of insulation. And then we're going to subtract the interior cylinder, which is pi A squared L. Because inside, we've cut out a piece that conductor fits in. All right, so that would be the charge of the cylinder that's sitting after A, but not going all the way out to B. It's part of the cylinder that goes out to B, but we're only interested in the part inside our box, which is a smaller box, so it only goes out to R2. Everything outside of it doesn't have an effect. All right, so if we rearrange this, E at R2 is going to be Q enclosed over the area of the Gaussian surface times epsilon naught. So that's going to be 2 pi AL sigma plus rho pi squared L minus pi A squared L divided by our area, 2 pi R2L epsilon naught. All right, now it's always good form to cancel out as much as you can. There's a 2, there's not a 2 on every term. Never mind, leave that there. There's a pi on every term. There's a pi here, and here, and here, and here, so those can go away. And there's an L on every term. Here, 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 and here, so those are gone. So we can reduce this to, this is equal to 2A sigma minus rho R squared minus A squared divided by 2 R2 epsilon naught. Okay, so if you've got a solid conductor inside an insulator and you're looking at the electric field somewhere inside the insulator, this is the equation for that. And unless anybody types in or asks another question, I'll just move on to the third part. Okay, so our third part has R3, goes all the way out to there, so now we're outside our cylinder. E at R3 times the area of the Gaussian surface at that point, Q enclosed over epsilon naught. All right, the area of our Gaussian surface at R3 is again going to be 2 pi R3 times L, and our Q enclosed is going to include sigma times area, which is the entire conductor, because we enclosed that earlier, and now we're even further out past that, plus rho times the entire volume of the insulator, which goes from B in to A. So Q enclosed is going to be sigma A, which is again 2 pi AL sigma, plus rho, and again we have a subtraction because we have a small cylinder inside that is not an insulator, but this time we're going to go from pi B squared L into pi A squared L, because now we're all the way out past the edge. Now we don't want to go all the way out to R3 because the insulator itself doesn't go out that far. This is just the enclosed charge, not all the volume inside of our cylinder. And the enclosed cylinder only goes out to B, it doesn't go all the way out to R3. So that's why we stop at B. All right, so if we rearrange this, we're going to have Q enclosed over A epsilon naught, which is going to give us 2 pi AL sigma plus rho pi B squared L minus pi A squared L divided by A, which is 2 pi R3 L and an epsilon naught. Okay, and again, pi's all cancel and our L's cancel. So E at R3 is going to be 2A sigma plus rho B squared minus A squared over 2 R3 epsilon naught. So almost the same equation we had before, but now we include all the way out to B squared instead of just R2 squared, and we're going out to a further distance. Okay, so if the cylinder were not infinite and had end caps, aha! Yes, but that is a very hard question. So Sarah's asking if the cylinder weren't infinite and we put an infinite, or we put another big cylinder around it, yes, then we'd have to account for the end caps here and for the sides here. But it turns out weird stuff, hard stuff to calculate starts to happen at the edges when you do that, so we will not do any problems like that. The only thing that ever fits entirely, the entire object inside your Gaussian surface is if you're doing a sphere. Otherwise, it's infinite in at least one direction. Yep, we're sticking with the easier ones here. Yeah, other questions? So all you have to remember for the Gaussian surface is basically pick an object, figure out which side the flux are going through, and then it's just a matter of rewriting your area for your Gaussian surface and your Q enclosed for everything inside your Gaussian surface. And then just rearranging and canceling anything you are certain is going to cancel. Yep. Yes, so the brute force equations are going to be an entire sheet on the exam. The 4 questions I gave earlier, or the 4 equations I gave on this first sheet, I'll be back over here somewhere. Yeah, so these 4 equations up here, the point charge, the line, the hoop, and the disk, along with a sentence saying y is the distance above the center, r is the radius, and so on. So you do not need to write those on your index cards. That would probably take up an entire side. I'm also going to give you constants, so you don't have to write down constants, or if you need any sort of, well, you guys should know things like nano and micro and centa and stuff like that. If you need to do any conversions like centimeters to inches or something, I'll do that. No, write down the volumes. Yeah, basically you need to know the volume of a sphere and a cube and a cylinder. And also the surface area of each of those.
I know this may be a very broad question, but could you just give us the potential questions? Like we just did a Gaussian surface.
Yep.
There'll be like electric potentials, just so we kind of can practice one of each on our own.
Those aren't going to be on the exam. Those will show up on the next exam. So the electric potential and the electric potential energy will be on exam 2 because we just started that.
Okay.
Yep. And I meant to push back the homework for that too. That's not due until Wednesday or Thursday. Let's make it due Thursday. And you don't need to know work or conservation of energy for this one either. Nope. Although it's good if you need the kinematics, I'll give you the kinematics equations, but you guys have used those before. And at the moment, the exam does not include kinematics, and I think I'm done writing it. Right, other questions? So you guys are good on everything that we did on the homework? Because those could also be on the exam, or similar ones. Okay, well, I'm going to hang out here for another 20 minutes or so, but if I don't get any more questions, then at that point I'm going to turn it off.
Can we do one? I know there are a couple of these on the homework where I believe it's like solving for the electric field where you have certain charges in a line.
Okay, yeah, there were a couple of those on the homework.
Yeah.
Let's see. Let's start with x direction. Let's call this 0 and 10 centimeters. Let's say there's a charge sitting here, QA, of -3 microcoulombs. And there's a charge over here, QB, -7 microcoulombs. And we want to know where the electric field is equal to 0. Okay, so let's start out with that one. So where is E equal to 0. All right, so this kind of problem, the first question is, what does the field actually look like everywhere? Well, there are three regions. We've got region 1 and region 2 and region 3, basically on either sides of the charges. All right, so let's take a look over here. We want to think about both of the charges one at a time. The electric field due to A, well, A is negative, so it's going to point towards A. So E due to A is going to point to the right. E due to B, this is negative, points towards B, also to the right. All right, let's look at this middle part here. In here, it points towards the negative QA, EA, and towards the negative QB, but here that's in opposite directions. And then on the left in region 3, or sorry, on the right in region 3, it has to point towards A, and it has to point towards B, so those are both pointing to the left. All right, now if you take a look at this, basically we want the electric fields to cancel each other out somewhere. The only place they can do that is where they point in opposite directions, because otherwise they're just going to make each other add together and get bigger. So it has to be somewhere in this region where the charges cancel each other out. I'm going to say it's at some distance x from 0, where x is somewhere between 0 and 10 centimeters. So 0 centimeters, smaller than or equal to x, smaller than or equal to 10 centimeters. And then I want to write my electric fields in terms of some distance x. So the electric field due to A is kQA over the distance between A and the point where it's equal to 0. So that is x squared. And A points to the left, so I'm going to put a negative sign on that one. EB points to the right, so this is positive KQB. And the distance between QB and where the field is being calculated, where it's equal to 0, is going to be the distance between A and B, 10 centimeters, minus the distance between A and our new charge x. So this is going to be 0.10 meters minus x squared. All right, and when I add these together, I've got 0. So minus kqa over x squared plus kqb over 0.1 minus x, entire thing squared, is equal to 0. All right, well, k shows up on both sides, so I can cancel those out. QA is 3 microcoulombs over x squared. And if I set these equal to each other, basically I'll add this one over to that side. So this is going to be 7 microcoulombs over 0.1 minus x squared equals 3 microcoulombs times x squared. All right, and I'm going to drop the microcoulombs for now just to save some space. So 7x squared, if I cross multiply, is equal to 3, 0.1 minus x squared. And then let's FOIL that out. So that's going to be 3 times 0.1 times 0.1, which is 0.01, minus 2x times that, so 0.2x, plus an x squared times our 3. So we've got 7x squared is equal to 0.03 minus 0.6x plus x squared. And then if we move all this stuff over to the other side, we're going to end up with 7 minus 1. So this is 6x squared plus 0.6x minus 0.03 is equal to 0. All right, and basically any of these problems you can, or anything like this where you're trying to find where e is equal to 0, you can always reduce to a quadratic equation. All right, so x is equal to minus b plus or minus b squared minus 4ac square rooted over 2a. So it's equal to minus b, which is 0.6 negative plus or minus 0.6 squared minus 4 times a, which is 6, times b, which is negative 0.0. Square rooted over 2a, so 2 times 6. Okay, so this should give us two different solutions depending on if we're using the positive or the negative. So that's minus 0.6 plus the square root of 0.6 squared minus 4 times 6 times negative 0.03, which works out well, divided by 12. So one of our x values is 0.0366. Or, if I put the negative sign in there instead, we get negative 0.1366. So basically our answers in centimeters are 3.7 centimeters or minus 13.7 centimeters. All right, now we got two answers out of this. Yes, exactly. That's a good point, Hannah. Yeah, so when I cancel these out, or when I cross multiply, the microcoulomb must cancel out anyway. So it doesn't matter that I'm ignoring them. Okay, so over here, we find that x is equal to 3.7 or negative 13.7. Well, now we have two answers. So which one is right? Well, only one of them suits our initial condition, which we said has to be between 0 and 10. So that means this right here is where they cancel out, right here at 3.7. This one is not actually an option. Because we took off the negative signs over here, this equation no longer recognizes that this is not a valid option. So it gave it as an option over here. But when we put the physics back in and say, oh, wait a sec, one of these or both of these have negative signs, we know it has to be in this region. This one doesn't actually work anymore. So we're left with 3.7. All right, are there any questions on that one? Okay, so question 6 from practice exam 1D. Let me see which one that was. Okay, I have to log back into Bridges. Let's see. Resources, previous exams, first exam, 1D, question 6. Okay, all right, so question 6 from practice exam 1D is very similar to another one we've already looked at. So let's just set it up. Let's see, we've got y coordinate, z, x. We've got a ring down here with some radius big R. And we've got a disk up here with some radius little r. And then we've got a point P where we want to measure the electric field, and then we're going to put a charge there. So there's some charge QA on the ring, and some charge QB on the disk, and then some charge QC will be over here at point P. And we want to find the force on QC. All right, now we know that the force is simply equal to Q times the field, where this is QC in here. So really what we want to start out by doing is finding the field at P. Okay, so we have an equation for the field due to a disk, E due to a disk, which is just a matter of stuff you can plug in, and E due to a ring, which again, you can just plug in because I'll give you both of those equations. And then what you need to do is basically say, all right, well, where are these pointing? So in this case, the ring...
Oh, sorry? You muted your screen because a couple of us can't see your screen anymore.
Sorry. Yep. Where is it? Okay, can you see it now?
No.
Oh, okay. Let's see. How about now?
There we go.
Okay.
Good to go.
I didn't realize I did that. Okay, so I've drawn this nice picture now. So we've got our ring down here with radius big R and our disk up here with radius little r. And basically what we want to do is just find the direction of the field here, because we have equations that will give us the equation of the disk, the equation for the E field of the ring and the disk. And I'm giving you guys those. You can just plug them in. All right, so it's just a matter of direction at this point. Now, I believe that this one, let's give it a negative charge, and let's give this one a positive charge down here. Okay, so at P, the E field due to the disk up here points towards the disk because it's negative. So E due to the disk points towards the disk. And the E field due to the ring at P also points up because it's pointing away from the ring, which is positive. So E field due to the ring. So in this case, you'd find the E field due to the disk at P, and then add the E field due to the ring at P to get your total E field. Total. And then your force on C is simply QC times E total. And then it's just a matter of plugging stuff into the equations. Okay, and we've already gone over one like that, so I don't really want to take the time to do it again. But it's very similar. We also used a disk and a ring that time. Any questions about that? Any other questions about how to set these things up? It doesn't really matter if I take it and move the whole thing sideways, then it's pointing in the X direction instead of the Y direction. That's really the only difference there. And these problems, when we do these, are always going to be along the same axis. You'll never have to worry about breaking things into components when we do problems like this. Yep. All right, and then there was another kind of question that was similar to the last one we did along a line, but it was a little bit different. And let's take a look at one of those. So for that one, you might have some QA and some QB. Let's see, located at 0. Let's say this is 15 centimeters. And then over here at 20 centimeters, we want the E field to equal 0. We want to know where to put QC so that this is true. Let's say QA is 4 microcoulombs and QB is minus 6 microcoulombs, and QC has some charge 2 microcoulombs. We want to know where we're going to put QC so that this is true, so that the E field at 20 centimeters is equal to 0. So this one's a little bit different in strategy than the previous one, so let's take a look. Okay, so here at E equals 0, we're going to have the E field due to A plus the E field due to B plus the E field due to C, and we want those all to equal 0. Which means we're going to have K QA over the distance between 20 centimeters and A squared, plus K QB over the distance between B and 20 centimeters squared, plus K QC over RC squared equals 0. All right, actually, let's put this in here as a plus or minus 2. We don't know which one it's going to be yet. Oh, actually, no, let's call it positive. Yeah, let's call it positive and see where we need to put it. All right, well, K shows up everywhere, so I'm going to cancel that one out. QA is 4 microcoulombs, and it's divided by RA to 20, so that's 0.20 meters squared, plus B is 6 microcoulombs, and this is absolute value, over the distance between this one and this one, which is 0.05 meters squared, plus QC is 2 microcoulombs divided by X, where X is the distance between this charge and QC. And it's either positive or negative. We're not sure yet. X squared. This is equal to 0. All right, and then the micros show up everywhere, so we can get rid of those too. All right, so we can say that 4 over 0.2 squared plus 6 over 0.05 squared is equal to minus 2 over x squared. All right, well, let's add up this side. Let's see. So that's going to be 4 divided by 0.2 squared. 4 over 0.2 squared plus 6 over 0.05 squared gives me 2,500 is equal to minus 2 over x squared. And all we're doing is looking for x squared, so let's cross multiply. 2,500 x squared equals 2. So x squared is equal to 2 over 2,500, and x is the square root of 2 over 2,500. Apparently I've given myself a very small number to deal with here. Okay, so the square root of 2 over 2,500 is 0.0283 meters. So it is 2.83 centimeters. Okay, so we've got 2.83 centimeters. This is our distance from that one to that one. But the question is it positive or negative? Yeah, so I called this positive. So the question is this value in this direction or is it in that direction? So let's take a look. The E field, let's see, the total E field at 20 centimeters due to QA, which is a positive charge, will point away. So E due to A is a positive number. E due to B, however, is a negative number, so it's going to point towards QB, which is EB. So really, this would be this minus this is equal to that. Yeah, so that would be 4 over 0.2 to the square plus, whoops, sorry, minus 6. Oh yeah, and then there's a negative 2. Sorry, I dropped that too. Negative 2, so that's definitely making this more complicated. Yeah. Okay, over 0.05 to the square. All right, so this should have been negative 2300 equals minus 2 over x squared. All right, there's our problem. Okay, so we're going to get negative 2300 x squared equals minus 2. So x is equal to root 2 over 2300. Okay, so square root of 2 over 2300, 0.0295 centimeters. Okay, and the net field here is negative. So right now, E net at negative 20 due to QA and QB is negative. It points in that direction. So if we want the net E field to equal 0 at this point, our new E field needs to be in the positive direction. All right, now we know that in order for the field to point in the positive direction due to a positive charge, it needs to be pointing away from it, which means QC has to be over here somewhere. QC, because it's positive and the field is pointing away. If we put it over here, QC would have had to be negative instead. And we already said it was positive. So our answer is going to be 20 centimeters minus 2.95 centimeters, which gives us, what, 17.05 centimeters? That's where we need to put our QC. It needs to be right there somewhere. Okay, sorry about that. Did that make sense? We got pretty much the right answer here to be subtracted, but when I actually put the negative thing in, sorry.
Like on how you knew that it's less than.
Yep.
20. I lost you on that part.
Okay, so the E field due to QA and QB together was negative, so it pointed in the right, or to the left. Are you okay on that part? So that total was 2300 when we put that negative sign in, because the one due to A points to the right, but the one due to B points to the left, and that one was bigger. So the negative field is 1, the net field is negative there. So if it's negative due to A and B, then due to C it has to be positive in order for that number to cancel to 0. So wherever we put QC, it has to result in a positive direction of the field at that location. Since QC is positive itself and the field always points away from it, if the field's pointing away from it by pointing to the right, that means QC has to be over here to the left somewhere, which means it's going to be to the left of this location. And our x is simply our distance to the left or to the right of 20 centimeters. That's what we solve for here. Because this is always going to be the distance between the 0 point and wherever we put QC. So once we came down with the answer, it had to be about 3 centimeters away. Which direction would it have to be? Well, if it's positive when we put it over here, its E field would have pointed to the right, to the left instead of to the right, and we need it pointed to the right. Did that make sense? Are you still confused?
Yeah. Just a little bit, but I'll look at it. No worries.
Just think, yeah. So basically the first thing I should have done is say which direction do the E fields point at that location. All right. So if these,
because at QA it's going out because it's a positive charge, and then at QB it's going towards it because it's negative. And since the negative 6 is bigger than the 4, that overall charge will be going to the right.
Charge will be going to the left. The net field will be going to the left because the 6 is winning. Yep. 6 is bigger than 4, and the number under it was also smaller. So this was definitely a larger influence than this one. And as a result,
Okay.
it's going off to the left. Yep.
Awesome. Okay, thank you.
Sure. Okay. Any other questions you guys want to see? I think that pretty much covers everything with the exception of maybe some conceptual questions. And those are similar to ones we've been asking on the PowerPoint, and you guys have been doing pretty well on those. Just a matter of things like where does the field point, where does the force point, where does the charge go? And I won't be giving you guys a two-dimensional force problem that involves components because those take too long to solve on an exam. All right, well, it looks like there's no more questions, in which case I guess I'm going to log out and I'm going to upload this to YouTube. It'll probably take an hour or two, at which point I'll send out an email with a link to it. Okay? Oh, flux, Gaussian surfaces, point charts. Yep, so basically you need to be able to solve a Gauss's law problem. You need to be able to apply the brute force solutions that I'll give you guys, the ones for a ring, a hoop, a disk, and use them to calculate electric fields and electric forces. You need to be able to solve flux problems, which is either stuff inside a box or going through a hoop or a ring or a surface. And yeah, manipulating point charges. That's pretty much all we've done so far. And then conceptual things like how charges move around. You might want to look back at charging by conduction and charging by induction. We did it at the lab and one of the first lectures as well. But I think you guys are pretty much good on that at the moment. And of course, how charges interact, which ones repel each other, which ones attract each other. Yep. Gauss's law, the flux, or let's see, what else did I say? Oh, the brute force method. So that's things like if you have the electric field due to a disk with some surface charge is Q over A, things like that. So we had equations for those written out. Okay, so these equations up here. So things like the field due to a point charge, the field due to a disk, the field due to a line, the field due to a hoop. So this is a hoop of charge. Yep, and those will be given on the exam. It's these equations. It's just a matter of, it's going to tell you things like y is the distance above the center, L is 1/2 the length, stuff like that. So those were the brute force equations, is what we called those collectively. Okay, great. All right, then I'll see you guys tomorrow.